Assalamu alaikum. In the past lecture, we were talking about method of joints. The second technique to solve or find the values for solve for the forces in the members of a structure is by method of sections. Now we can analyze the plane truss by method of joints as we have done in the previous lecture. We need only two of the three equilibrium forces, or I mean three equilibrium equations. Now, because the procedure involves concurrent forces at each joint, we can take advantage of the third or moment equation of equilibrium by selecting an entire structure of a truss for the free body in equilibrium under the action of a non-concurrent system of forces. This is the basic technique of the method of section. And this method of section has the basic advantage that the forces in almost any desirable member may be found directly from an analysis of section. Now, thus, it is not necessary to produce with the calculations from joint to joint. It is not necessary to you have to proceed from joint to joint. You can directly reach the member in question. In choosing a section of truss, we note that in general, not more than three members whose forces are unknown should be cut. So you should not cut members in any section. You should not cut number of members. You can say that those members should not be superseded whose values are unknown. For instance, in a structure, if there are 4, 5, 6 members and you want to cut it from there, then the maximum number of unknown forces in a member should be not more than 3. So, in better understand by some illustration method, let us start how we are going to illustrate this thing. The method of section will be illustrated as you can see in the figure on the left. Let me select the proper pen. Now this is the same figure which we have used for the method of joints. The truss shown is already a reference for method of joints, and you have already solved for the method of joints. The first thing is the external reactions are first to be computed with the method of joints by considering the truss as a whole. You can use as a whole. This means you have to find the value of R1, L or L2 or any external member forces acting on this truss. Now let us determine the force in the member. So we are going to determine the force in the member BE, for example. Directly invite this force member. An imaginary section as indicated by dashed line, you can see in figure A, is passed through the truss, cutting it into two parts. Right here, two parts. This section has cut, now this particular section cut three members whose forces are initially unknown. In order for the portion of the truss on each side of the section to remain in equilibrium, it is necessary to apply to each cut member the force which has exerted on it by the member cut away. Now, for simple truss composed of straight two force members, these forces, either tension or compressive in nature, will always be in the direction of the respective members. If you look at the left hand section, it is in equilibrium under the action of the applied load L and the end reaction R1, and the three forces exerted on the cut members by the right hand side section, which has been temporarily removed for our analysis. See, external forces. We can usually draw the forces with their proper sense by visual approximation of the equilibrium requirements. Balancing the moments about, now let us start with balancing the moments about point B for the left hand section. The force EF is clearly to the left. If we look at this thing, we can start from B. You can see that the the EF has to be on the left. which makes it compressive because it acts towards the cut section of the member EF. The load L is greater than the reaction R1, so that the force BE must be up to the right must be up and to the right to supply the needed upward component of the vertical equilibrium. The forces BE is therefore tensile, since it acts away from the cut section. With the approximate magnitudes of R1, L in mind, we see that the balance of moments about point E requires that BC to be on the right. It means moving away from right section. A, a casual glance at the truss should lead to the same conclusion when it is realized that the lower horizontal member will stretch under tension caused by bending. The equation of moment about joint B eliminates three forces from the relation, and EF can be determined directly. The force BE is calculated from equilibrium equation for y direction. Finally, we determine BC by balancing moments about point E. In this way, each of the three unknown has been determined independently of the two. The right hand section of the truss, as you can see in the figure B, is in equilibrium under the action of R2 and same three forces, that is EF, BE and CB, that are in the cut section. See, the proper sense of the horizontal forces can easily be sensed from the balance of moments about point B and E. Now, some considerations are important. In the essence, to understand that in the method of section, an entire portion of the truss is considered a single body in equilibrium. The forces in members the forces in members internal to the sections are not involved in the analysis of the section as a whole. The free body diagram and the forces acting externally on it, the cut sections, is preferably passed through the members and not the joints. So the entire portion of the truss can be used for calculations, but the one involving smaller number of forces will usually yield simpler solutions. You have to keep this in mind. Some cases, the method of sections and method of joints can be combined to get a better effective solution. For example, suppose we wish to find the force in a central member of a very large truss, or you can say further suppose you can say the further complication could be that it is not possible to pass a section through these members without passing at least four unknown members. This means number of unknown members are more, and the more sensible approach for you to is to calculate some of the members by using method of joints. It may be possible to determine the force in nearby members by method of sections and then progress to unknown members by method of joints. Such combination of two methods uh, can uh, can be used to simplify your problem. The moment equations are used to greater advantage in method of section. One should choose a moment center either on or off the section through which as many unknown forces as possible can pass. It is not always possible to assign a proper sense of unknown forces when the free body diagram of the section is initially drawn. Once an arbitrary assignment is made, a positive answer will verify the assumed sense and negative result will indicate that the force is in the sense opposite to that of initial assumption. An alternative notation preferred by some, or you can say, is uh, you can assign a common positive or negative to all the forces. and you can assume the forces, if it is positive, can be in tension, and let the algebraic assign, or you can say that when you solve these calculations, the algebraic relations will assign or distinguish positives from the false positives, the true positives from the false positive, and you can identify those false positive as your compression. On the other hand, the advantage of assigning forces is, in the correct sense, on a free body diagram or section is whenever is wherever possible is emphasized. It improves your engineering skills and shows your engineering knowledge. It is preferred in your common practices to assign a proper or more, you can say, evolved guess of the force direction.